So what noise do racing cars make? Make it yourself now if you'd like to, but basically cars, as they go along, go meow, and this is due to the Doppler effect. Now we can think about the Doppler effect in terms of maybe some kind of duck which is swimming across a pond. Now I don't actually have a Lego duck, but I do have this little Lego chicken here. So what I'll imagine is this is some kind of duck. And basically if you have a duck and you throw some bread into the pond, all of the ducks start swimming towards you. And what we see is the pattern of the ripples that actually come out from the ducks. And what we find is that the ripples look a bit like this. Okay, excuse my kind of sort of shaky lines. But basically what we find is in front of the duck which is swimming, we have quite a short wavelength, a bit like this. Behind the duck, the wavelength gets quite long. And this is compared to maybe the kind of wavelength that we started with, the kind of sort of the wavelength of a normal duck which is just sort of bobbing up and down in the water. And this is due to something called the Doppler effect. Now the Doppler effect is due to the change in wavelength and also the change in frequency due to an object which is moving and emitting waves. And the Doppler effect, basically it's really, really important. You know, this is in terms of cosmology, gives us a fantastic insight into what happened to the universe a long time ago from what we can actually observe at the moment. So basically the Doppler effect is when the wavelength changes. It's useful in cosmology as well as when we look at things like blood sonography using ultrasound. So this video is really about the starlight that we observe. Now with stars, all we can really do is just observe them. All we're doing is just looking at them and trying to kind of analyse the light that we see. And basically, if you take the sort of the white light that you see from a star and you put it through either a prism or in most cases a transmission diffraction grating, and I do have a video up here that I've linked to and it's also down in the description below. But for some reason, my video on diffraction gratings has been my most popular video, even though it's not necessarily the most interesting. But you know, I think it is quite a useful video. But basically, you put white light through a transmission diffraction grating, and what you see then is a whole spectrum of colours. But Joseph van Fraunhofer in about 1814 found that when you look at starlight, there are certain lines which are missing. Now we know that this is now effectively an absorption spectra. The reason is that there are various elements within the sun's atmosphere that absorb certain wavelengths of light, and this is due to the electrons jumping around from one level to another. So basically, certain elements in the atmosphere of the sun cause there to be certain absorption lines within the spectra that we see. Now, one of the basically something which is we assume and is kind of that fits all the science we know, is that physics is the same everywhere in the universe. So when you have hydrogen on Earth, it's the same as the hydrogen in the sun and the hydrogen around the rest of the universe, because we sort of have these protons and electrons that kind of orbit around. But basically what they did was they looked at some other stars and they found that this is the kind of pattern that they got. They looked at the white light, they looked at it through prisms and diffraction gratings, and they found these very distinctive Fraunhofer lines, as they're called, but they appear to be in a different place. So two explanations. First of all, there could be different elements in this kind of part of the solar system. Maybe they don't have hydrogen like we have, they've got something else. But as more and more bits of starlight were looked at, they found that these same kind of lines, the ones that we see with the emission spectra here, were repeated. But this time, they tended to be shifted towards the red end of the spectrum. And this is a really, really important piece of evidence. Basically, by looking at starlight, you can actually see that the Doppler effect in action. And it's due to these absorption lines here, which are being shifted towards the red end of the spectra. And basically what you can do is you can actually measure that change in wavelength. And if you know that change in wavelength over the wavelength that it was originally, this then tells you about how fast that object is moving. And this is the value of v. Now because we're talking about the speed of light, everything was originally travelling at c, the speed of light, but the thing that was emitting this light, the star itself, was actually moving. And basically, if something was moving away, then this is when the wavelength would get longer, and this is what we call the recessional velocity. So when you have something which is receding, the velocity basically means that the wavelength gets longer. And this is what we call redshift. And the vast majority of things in our galaxy tend to be redshifted. That means everything is moving away from us as the Earth. Now we can also say that this is also equal to the change in frequency over the original frequency. So that's just another way of looking at this equation. And some things are blue shifted, some things in the universe are moving towards us. And that might be nearby stars or perhaps some, one or two galaxies. But by far and away, what they found when they looked at all the starlight and they observed it was that every galaxy tends to be moving away from the Earth, and the galaxies which are further away tend to be moving away faster. And this is where the work that Edwin Hubble did in the sort of 1920s or early part of the 20th century really came in. And that gave us then a bit more evidence for what might have happened previously before we got to this point in history. So, just to summarise, what we have is we have Fraunhofer lines in the spectra that we see from sunlight. These Fraunhofer lines tend to be shifted towards the red end of the spectrum due to the Doppler effect, and this is called redshift. And if we can measure the change in wavelength or the change in frequency, we can then work out how fast that thing is moving away or towards us. So keep watching to see a bit more about how this is useful and how this gives us evidence for the Big Bang.